Hi, this is another video for another lesson in General Physics 1, and we will focus on applying Newton's laws of motion. And one of Newton's laws is of course law of inertia. That's the first law, which states that an object at rest will continue to be at rest, and an object moving with a constant velocity will continue to move in constant velocity unless and otherwise there is an equal and unbalanced external force acting on that object. Now, with that premise, if all of the forces are balanced, then we will arrive at an equilibrium. So that will be the first condition of equilibrium. If the object is having a net force of 0, then we can consider that object in equilibrium. And equilibrium can either be static or dynamic, which means rest or object at rest and object moving at a constant velocity respectively. So if the object is moving with a constant velocity, then we call that as dynamic equilibrium. And if the object is at rest, then that is known as static equilibrium. If objects are in equilibrium, then therefore acceleration is also 0 because your net force is equal to 0. So again, in equilibrium, all of the components of the forces must be equal to 0, or they must result to 0. So that's both for static and dynamic equilibrium. So let's look into some examples to illustrate the first condition of equilibrium. So we have here two balls are hanged one after the other as shown in the figure. The upper ball is 0.35 newtons while the lower ball weighs 0.28 newtons. Solve the tension in each string supporting the ball. So what do we need to do to solve for the strings that are acting or to solve for the tension force that are acting on each of these strings? So first, the very first thing that we need to do is we need to draw a free body diagram so that we can factor in all of the forces that acts on an object. Looking at this diagram and looking into the word problem, we can conclude or we can infer that our objects are in static equilibrium because they are hanging, they are not moving. And since we have two balls, then we will illustrate or we will draw two free body diagrams, both for weight 1 and for weight 2. So we have here the first ball and then we have here the second ball. So we have the first ball. First ball, of course, you have just the ball, the upper ball. You have the tension. Let's label that as tension 1. Then you also have the weight 1. Now, aside from tension and weight 1, you also have another tension here. Why? You have here, this is your ball 1, and you have here a rope exerting a force and another rope exerting a force below ball 1. Remember that strings exert forces or exert force on both ends of the string or on both ends of the cable. So that's why you have here a string below weight 1, and therefore that string also exerts tension force to the ball. Now for weight 2, since you have one string above it, that's tension 2, that's the tension from rope 2, and weight 2. So these are our free body diagrams. And remember, they are in static equilibrium. And when an object is in equilibrium, again, the total forces acting on that object must be equal to 0. So we know that the net force here is 0, and the net force here is also 0. But what would be the net force equal to here when we express it in all of the forces? Remember that when we say net force, it's the net force is the sum of all the forces acting on an object. So what are the forces acting on an object? Our example is simple because the forces are just in one dimension, that is all in the y-axis. So our net force here will be equal to, we have positive tension because it's going up by convention. Forces that are going up are considered as positive. Minus tension 2 minus weight 1. And on the other hand, on this part, our net forces here is equal to positive tension 2 minus weight. So now what we can do here to solve for our tension, we need to solve first for, or we need to use the equation that there's only one unknown variable. We know what the value of F net here, that's 0. So therefore this equation can become T1 minus T2 minus weight 1 is equal to 0, and this one T2 minus weight 2 is equal to 0. Now in this equation, only tension 2 is unknown because we can solve for, or we know weight 2, and as stated in the problem, weight 2 is 0.28 newtons. Therefore, tension 2 is equal to weight 2 if you transpose this one. So if tension 2, or if weight 2 is equal to 0.28 newtons, then therefore T2 is also equal to 0.28 newtons. So now we know T2. Now in this equation, there are three expressions, or there are three variables. You have tension 1, tension 2, and weight 1. We don't know tension 1, but we know tension 2 and weight 1. Therefore, we can use, or we can already substitute all of the known variables here and only be left with one unknown variable. And the equation will be T1 will be equal to T2 plus weight 1, because you will transpose this one, and they become positive. So T1 is equal to, your tension 2 is equal to 0.28 newtons plus weight 1 as stated in the problem, that is 0.35 newtons. So 0.28 newtons plus 0.35 newtons, that is 0.63 newtons. So therefore, the tension force that is acting, or the tension force that is exerted by the string, the first string, is 0.63 newtons. And the tension here is 0.28 newtons, which makes sense because if we observe, or if we look into this diagram, we know that the upper rope, or the upper string, carries both weights 1 and 2. But for the second string, it only carries weight 2. Therefore, it makes sense that the tension exerted in the first string is bigger compared to the tension exerted by the second string. Let's look into another example. So the two ends of a rope is fastened at 2 points on the ceiling, a distance of 13 meters from each other. If a load of 200 kilograms is placed, as shown in the figure, find the tension of the rope. So what do we need to do here? Now for this problem, we only have one load with two different strings, or with two strings that are acting on that same load. So we need to solve for the tension exerted by the ropes. So let's label this as our tension 1 and tension 2. Always, what we need to do first always is we need to draw a free body diagram so that we can factor in all of the forces that acts on our object. So if this is our, let's draw the forces here. If this is our load, then therefore definitely there is weight, right? And then you have your tension 1 here and tension 2. If we illustrate that in a Cartesian coordinate plane, or if we draw a free body diagram for that, you have there the weight, And remember, in the Cartesian coordinate plane, you have the x and y axis. Now, your tension 1 is not really, how do we say it? Not really just laying in one axis because it's acting on both x and y axis. Therefore, your tension 1 has components. So for your tension 1, it has your T1x at T1x, and this also has your T2x. Then you have your T1y and T2y. So those are our components. Now, of course, our net forces here is still equal to 0. Why? Because the hanging load is neither, or is not moving. And if it's not moving, then therefore it's in static equilibrium. So we can form an equation out of the different components here. We know that the total forces along x will be equal to, since these are opposite, you have T1x, which is negative because it's directed towards the left, plus T2x. Now for the total forces along y, then that will be, you can see here, positive T1y plus positive T2y minus weight. Now, we cannot proceed for the solution here because, or we cannot proceed with our solution here because, again, you have here a tension force, or we have here both of the tension forces that are acting both on the x and y axis. Therefore, we need to solve for the angle in between these, or the angle between T1x and T1 and T2x and T2, so that we can solve for, or we need to solve for the angle so that we can solve for the components. Now, what will be the angle here equal to? So we know the value of the hypotenuse. And if you remember our lesson in solving for vector components, so you can easily identify, or you can easily conclude that to solve for T1x here, your T1x will be equal to T1 cosine theta 1. So we label this as angle 1 and angle 2 so that we don't get confused. And your T1y here will be equal to T1 sine theta 1. And on the other side, you have your T2x should be equal to T2 cosine theta 2. And you have your T2y, which should be equal to T2 sine theta 2. What's next? So we now have the expression for the forces along x and the forces along y. So let's solve for the angle here. What will be the angle equal to? Remember that if you can see here, we have the distance, or the length of the ropes. So if we look into this as displacement, if we have imaginary lines there, if this is 10 meters and this is 8 meters, then we can use this two values to solve for the angle. And what will the angle result to? So we have, if this is your angle 1, then you have your adjacent side and you have your opposite side. And that, if we have the adjacent and the opposite side, then we can use what trigonometric function? We can use tangent. So the inverse tangent of opposite. What's the opposite here? It's 8 meters divided by 10 meters. So theta 1 tangent negative 1, or the inverse tangent of 8 divided by 10, that will give us a value of 38.66 degrees. Then for theta 2, we have inverse tangent. So if this is 3 meters and this is still 8 meters, so this will be 3 meters over 8 meters. Therefore, theta 2 will be equal to 69.44 degrees. So we now have the value of our angles. We now also have an expression for the forces or the net forces. Now, remember, since this is in static equilibrium, then we know that the total forces along x and the total forces along y will be 0. So these are all zeros. Then, what's next? So we can use, or we can use one of the equations to be substituted in one equation. So we can transform this equation into t1x is equal to t2x. And then you have here t1y. So you have here the equation for, oops, let me erase that. You have here the equation for the y components. Now for your y and x components are not equal, or I mean the the x component, the x components will be equal. Why? Along the x, we have no motion, and there are only two opposing forces. And if there are two opposing forces and the acceleration is 0, therefore your total forces or your t1x is also equal to t2x, which is expressed in the equation that we have derived. Now we have here t1y and t2y, and we can see here an equation that we can use to change the expression into the value that we are trying to find, which is tension itself. So in transforming this equation, we just need to substitute the variables here. If t1y is equal to t1 sine theta 1, then we have, let's transpose this first, so that's w, which or weight, will be equal to t1 sine theta 1 plus t2 sine theta 2. So you have t1 sine theta 1 plus t2 sine theta 2. So that's t1 and t2. For this equation here, you can further transpose this one into, we have t1x here, this one, that is t1 cosine theta 1 equals t2 cosine theta 2. So for one equation to work, we need to make all unknown variables just one, or we just need one. We must make an equation with only one unknown variable. However, both of these equations has two unknown variables. Both of these equations have two unknown variables. So we can use this one to be substituted in a variable here. So let's take, for example, t1. If we transpose this one on the other side, you will get t2 cosine theta 2 over cosine theta 1. So if t1 is equal to this expression, then therefore we can substitute that in this expression, which will give us, let's make a division here, so you have t1, or that's weight, is equal to, if t1 is equal to that expression, that's t2 cosine theta 2 over cosine theta 1 sine theta 1 plus t2 sine theta 2. Sine theta 1 divided by cosine theta 1, sine divided by cosine, that is tangent. Therefore, W is equal to T2 cosine theta 2 tangent theta 1 plus T2 sine theta 2. Now we need to just isolate the expression T2 so that we can solve for T2 and we can factor that out in this expression. Therefore, W is equal to T2 multiplied by cosine theta 2 tangent theta 1 plus sine theta 2. Then, to isolate T2, then we transpose that one again. That will become T2 is equal to weight all over cosine theta 2 tangent theta 1 plus sine theta. So that is now our equation. So let's just free some space here. So our derived equation is tension 2 is equal to the weight divided by the cosine of angle 2 multiplied by the tangent of angle 1 plus sine of angle 2. So what we need to do here is just to substitute our known values. Again, our equation T2 is equal to weight over cosine theta 2 tangent theta 1 plus sine theta 2. So T2 is, what is weight 2? We know that weight 2 is equal to mg. So if weight is equal to mg, then that is 200 kilograms multiplied by 9.8 meters per second squared over cosine angle 2, as we can see here, is equal to 69 cosine 69.44 times tangent angle 1 is 38.66 plus sine 38 point, oops, it's not fit. Let me rewrite that one. So you have tangent 38.66 plus sine 38.66. So if that's our equation, then you can just input that in your calculators and that will give you an answer of 1610.18 or approximately 1610.18 newtons. Therefore, tension 2, which is this one, is 1610.18 newtons. So this is our answer. Now we're not yet done because we need to solve for T1 as well. And remember earlier, we have an expression for T1. If you remember one of our equations earlier, we know that T1 cosine theta 1 is equal to T2 cosine theta 2, right? Because all of these x components are equal to each other since they are the only forces and they are opposite. Therefore, T1 is equal to T2 cosine theta 2 over cosine theta 1. So we just need to substitute the known value since we already know T2 and we know the value of angle 2 and angle 1. So it's important that you are able to know all of the forces that acts on an object so that your equations will be correct. Because as you can see, we don't have a standard or we don't have a consistent formula for each of our problems because we need to make a formula out of all of the forces that acts on the object. So where are we? So we have here T1 is equal to T2 cosine theta 2 divided by cosine theta 1. So substituting your values, you have T1 is equal to, T2 is 1610.18 newtons. Cosine, theta 2 is 69.44 all over cosine 38.66 degrees. So if this is our equation, if you input that in your calculator, then T1 will be equal to 724.16 newtons. So therefore, your tension 1 exerts a force of 724.16 newtons at 38.66 degrees, and tension 2 exerts a force of 1610.80 newtons at 69.44 degrees. If you look into the illustration, so you will see that the shorter string exerts more force or exerts greater force compared to the longer string. That's it for our lesson on first condition of equilibrium. So watch for the second video. You can watch the video on second condition for equilibrium so that you can complete the lesson for equilibrium. Thank you very much for listening and see you.